Sir, question related with load capacity of uh, column,
Okay,
a
yeah,
stone column.
yeah.
There was basically one numerical,
Hmm.
lecture numerical, first
Yeah,
numerical. Uh, there was actually load capacity actually equated for individuals and for group. Kindly
okay,
show that
yeah.
questions.
Okay, yeah, let me open that presentation. Just give me a minute.
Yes, sir.
Can you see my screen now, Vishal?
Yes, sir. Yes, sir.
Okay, right. Let me just go to the particular slide. So are you referring to this load capacity of column?
Yes, sir.
Yes, okay, okay. Just let me. So the load capacity of a single column consists of three parts. One is the load capacity due to the native soil itself, confinement by the native soil, and then the load capacity of column due to the surcharge effect, and then the load capacity of the clay soil within the unit cell. Okay, because there are. Okay, let me just. Let me just show you the unit area. Yeah, okay. So if you have either a square pattern or triangular pattern, right? You'll have a unit cell area, and within each unit cell, there is a column of granular material, and then there is soil in between. Okay? And this particular equation that you have, okay? So this is the load capacity of the column due to confinement by the native soil, and the confinement from the native soil is because of the sorry because of this radial pressure plus 4 times Cu. Okay, that is actually the sigma R naught is the initial effective radial stress. Then 4 Cu is basically the bearing capacity of the soil that is surrounding the column. And this limiting radial stress, sigma R naught, is K naught times 2 gamma prime times D, because we assume that maximum lateral pressure is acting at depth of 2D. That is where the maximum bulging has taken place. So this, the sigma V is, sigma V is limiting radial stress, that is sigma R naught plus 4 Cu times Kp of the column, right? And then similarly, the load capacity because of the uniform pressure applied on the soil and the average pressure because of the surcharge pressure is 1 plus 2 K naught by 3 times Q safe, where K naught times Q safe is the lateral pressure and Q safe is the vertical pressure. And because of this, the load capacity is once again Kp times delta sigma, right? And divided by some factor of safety. And then the load capacity of the soil is area of the cell minus area of the column. In triangular pattern, the area of the cell is 0.866 times s square. And in the square pattern, it is only s square. Okay? And so the load capacity is Q safe times the area of the soil. And that is Q1 plus Q2 plus Q3, and that should be equal to the applied pressure multiplied by the area of the cell. Okay, is this clear?
Yes, sir.
And out of the 3 failure mechanisms, we do the analysis only for one, the first case, because the second and third, they pertain to much different conditions. And especially the third one is more like a punching shear failure, but that happens only in the short columns, but we don't have any short columns. Okay. And if you look at the numerical example, I think there is a I'm not sure where it is, but I think, yeah. Let me just open another file. Yes. Can you see the MS Word text on my screen? Vishal?
Yes, sir. The screen is actually not visible, sir. Only
It's not.
unit cell tank is visible.
Okay. I think I will have to share it once again. Just 1 minute. I know the problem. It is stop sharing. I think now are you able to see my?
Yes, sir. Yes, sir.
So this is numerical example for the same problem. Okay. And I think I will share this. I don't know whether it should be available on in the resource material. Were you able to download it? If not, I will share this once again. Basically, let me just explain to you. So we have a soil that has undrained cohesive strength of 40 kPa and 10 meters thick. And we want to provide a stone column of diameter 800 mm The applied pressure on the soil is 150 kPa, and the friction angle of the stone aggregate is 50 degrees, and the K naught is taken as 0.5. And we want to determine the center to center spacing of the stone columns for unreinforced conditions. Okay. And so when your C is 40, ultimate bearing capacity of the soil is 5.14 times 40. 5.14 is our NC, and that's 205. And with a factor of safety of 2.5, the safe bearing capacity is 85 kPa, right?
Sir, here factor of safety not given, but you have taken
Uh,
in lecture also
Actually, this
2.5.
is from the IS code, IS 15284. Um, I think it is explained in my lecture, but I will share this IS code also. That's uh, after this session is over, I will share both the resource material. Okay, and
Sir, in examination, how we need to this remember,
in the
or
examination,
randomly we can take any value.
um, no, if it is an examination, all the factors will be given, right?
Okay, sir. Proceed, sir.
Because it's a multiple choice question, and unless all the data is given, you will not be able to match any of the solutions. Okay?
Yes, sir.
So the safe bearing capacity of the soil is 85 kPa, right? But we want to apply a pressure of 150 kPa. So we need to reinforce the foundation soil with stone columns to be able to support larger pressure. So the capacity of the stone columns based on the bulging is, there are three components. Okay? And the first component is because of the confinement of the column by the surrounding soil. And the sigma RL limiting pressure is sigma R naught plus 4 Cu. Okay? And sigma R naught is K naught times sigma V naught. Okay? And 2D is 1.6 meters below the ground level. And our sigma V prime is 1.6 times um, okay, and I have assumed effective unit weight of the soil is gamma prime of 10. Okay? So 16 kPa, and the Kp column is 1 plus sine phi by 1 minus sine phi, that is 7.55. And our limiting radial pressure is 0.5 times K naught times sigma V prime, that is 16, plus 4 times Cu, that is 168. And so our sigma V is 168 times 7.55, that is 1268. And sigma V save is with a factor of safety of 2, it is 634. So the safe load capacity on the column is 318. Okay. And then the surcharge effect is Q safe is 85 kPa. And so the delta sigma R naught is 85 by 3 times 1 plus 2 K naught, that is 56.7. And so delta sigma V is Kp times this pressure. So this is 428, and then with a factor of safety of 2, that is 214. And then due to the surcharge effect,
Sir, delta sigma V safe always be 50% of delta sigma V.
yes, yeah, actually in the IS code, it is given. that we need to apply a factor of safety of 2 for getting the safe load.
Okay.
So it is taken with the same factor of safety. And so the column capacity, because of the surcharge effect, is 107. And then the intervening soil area is in a triangular pattern. The area of the soil is 0.866 s square minus pi d square by 4, or in the square pattern, it is s square minus pi d square by 4. So the load capacity on the intervening column is A ground multiplied by Q safe. So if you equate all these things, Q1 plus Q2 plus Q3, and equate that to the applied pressure of 150 multiplied by the unit cell area, that is 0.866 times S square, or 150 times S square in the square pattern. So in the triangular pattern, we get a spacing of 2.6, whereas in the square pattern, we get a spacing of 2.4 meters. Okay? And then we also have to look at the settlement reduction because of placing these stone columns. And the stress concentration factor N is actually this settlement reduction factor is given as 1 by 1 plus N minus 1 AS, where N is the stress concentration factor, that is sigma of the stone column divided by sigma of soil. And so this comes to almost 10. And the area replacement ratio is AS divided by the unit cell area. AS is the area of the stone column, that is pi by 4 plus 0.8 square. And the unit cell area in the case of triangular pattern is 0.866 times S square, that is 2.6 meters in the triangular pattern. This the replacement ratio is 0.085. That is 8.5% of the soil is replaced by stone columns. And so our settlement reduction factor comes as 0.57. So the settlement of the stone column treatment will be 57% of the settlement of the untreated ground. And similarly, in the case of the square pattern also we can work. Yeah,
Oh, sir, here actually importance of this stone column
yeah,
is emphasized by this settlement reduction factor, because without stone column, it suppose untreated ground, this settlement have S, but
yes,
after a stone column it becomes 0.57 of S, like
that's
this.
right. Yeah, yeah. So for example, if
Oh,
the settlement of the untreated ground is 100 millimeters, settlement of the treated ground will be 57 millimeters.
oh, okay.
Okay.
Thank you, sir. Thank
And
you.
so if you want to further reduce the settlement, we can reduce the stone column spacing. See here, we have calculated a spacing of 2.6 meters in the triangular pattern. And let's say you reduce it to 2 meters, then your settlement reduction factor um, will be will be actually much higher, and so um, your settlement will be lesser. The beta will be lesser, and you can extend the same thing with providing the stone the geosynthetic encasement. Let's say now we provide a geogrid having a secant modulus of 2500 kilonewton. And this is a typical geosynthetic having a tensile strength of 250 kilonewton at 10% strain. Okay? And delta sigma 3 in terms of axial strain and then the modulus is given like this. This was derived in the lecture. Okay? And if you assume that the axial strain of the column is limited to 2% and our diameter is 0.8 meters. So for these conditions, our increase in the confining pressure because of the geosynthetic is 64 kPa. And so this 64 kPa, we will add it to the previously calculated confining pressure of 88 kPa, right? So if you add this 64 to 88, it comes to 152 kPa, and our spacing slightly increases. Um, yeah, actually, this is this is with done with clay strength of 20 kPa. So we see different numbers. Yeah, okay. The Cu is taken as 20, and with the geosynthetic, the spacing comes to 1.8 meters, and without the geosynthetic, the spacing in the triangular pattern comes to 1.5 meters. Okay? Yeah, 1.5 meters. And with the geosynthetic, the spacing is slightly increased to 1.8 meters. Okay? And so the settlement reduction factor is a 0.26, that is 26% of of the uh, the the settlement of the untreated ground. So I will circulate this set of calculations along with you require, I think I've already discussed the code IS 15284 in the lecture. But anyway, I'll circulate this.
Sir,
Yeah,
basically, in structural analysis or solid mechanics, for
yeah,
analysis of anything, we have
yeah,
used Young's modulus. But here, in case of during calculation of additional confining pressure, we are
yeah.
taking secant modulus of that swell particles or that stone column. Sir, why you are not taking Young's modulus?
Yes, okay, okay. Just 1 minute. Let me just come back to my presentation on the stone column. Actually, when it comes to the soil, see this Young's modulus is only good for materials that are like steel and concrete. But when it comes to soil, our modulus is much smaller, and it's varying a lot. If you look at the pressure settlement graph, it is varying a lot. So at the larger settlements, we get lower modulus. Okay? So the secant modulus is the tangent slope of the pressure versus the strain graph at a particular strain level. Okay? And so in order to limit the settlements to some value, or the strain to some value, we take the corresponding secant modulus. Is that clear?
Yes, sir. Yes, sir.
So basically, you should not compare the soil with materials like concrete and steel because there the modulus is very high, and because of that,
Sir, basically,
this
what actually before 1 month, when
yeah,
I was actually simulation in Plaxis 2D,
yeah,
actually for multi-channel surface wave velocity, actually I
yeah,
was actually doing actually calculating steepness of the strata
yeah.
of nearby NIT Arunachal Pradesh landfill area.
Mhm.
Actually, I have used MSW. In that, I have used elastic modulus of that soil strata for the simulation of calculation of factor of safety and total displacement like that. That's why I was thinking, sir, why we have used secant model.
Yeah, actually, see, in this type of wave propagation analysis, your strains are very, very small, maybe of the order of
Oh,
0.1% to 0.5% strain. But when it comes to the
oh,
soft clays, your strains are very large, 5%, 10%. So there we have to
yes,
necessarily
yes.
take a secant modulus. Because even here, if you draw tangent, the initial modulus, uh, the the curve is very steep. But if you draw any secant modulus, the slope is much lesser.
Oh, yes, 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 sir.
Okay.
Okay, sir. Thank you, sir.
Today we have only two students. Regina, do you have any questions?
Yes, sir. I have given some questions in chat. I will discuss over
Oh,
here.
in the chat. Okay. Can you please discuss?
Yes, sir. Yes, sir. First one is regarding the calculation of O90, sir. In apparent opening size test,
Yeah.
there was one question given in which O85 and O50 was given. How we can calculate O90, sir? Can you please explain about it?
Okay. Let me just check up.
Okay, sir. Okay.
Yeah. Let me open that presentation.
Okay, sir.
Um, okay, just one minute. Just 1 minute. Just one. Let me just,
Sir, it was given in 10th lecture. 10th one.
yeah, okay. Okay.
Ah,
Yeah. Okay. Thank you. Let me just open. That's what I was looking for. Um, lecturer.
sir, it was together with filters, functions of filters.
Okay, okay. I think let me just, I'm not able to find where exactly, but let me just open the, yeah, filtration. Yes, yes. Okay, okay. Right, I found it. Just 1 minute.
Okay, sir.
Yeah, can you see my screen? Filtration of soils using the
Yes,
geosynthetics.
sir. Yes, sir.
Okay, right. Okay, let me just just stop me.
Yeah, sir. Here.
Okay, here.
21st slide. 21st.
Okay, yeah,
21st. Yeah.
this one. Okay.
Yeah.
So,
Exactly, sir.
yeah, O90 of the geotextile should be less than D85 of the soil. That is the piping limit. And the
Okay.
permeability limit is O90 should be greater than 15 D15 of the soil.
Okay, sir.
And the D15 and all these things are very simple, like our so this is our grain
Yes, sir.
size
Ah,
distribution
that okay.
analysis.
That
Okay.
okay.
So
Corresponding.
D15 is corresponding to 15% finer, and D85 is corresponding to 85% finer. Okay. Okay. And so this D15 and D85 and D60, these are all obtained from our grain size distribution analysis.
Yes.
So here what we are saying is our to prevent the soil particles from escaping, our O90 of the geotextile should be less than or equal to D85 of the soil. And the permeability criteria is at the same time, our opening should be at least greater than 50 microns or D15 of the soil, so that our geotextile has enough large size opening through which water can flow.
Okay, sir. I think last question for the assignment given in week 10. There was a question given D85 and D15 values were given, and
Yeah.
we were asked to find out the O90 value.
Yeah, O90 to satisfy these limits.
That is
See,
less than
yeah,
D85.
O90 should be less than D85 or greater than 50 microns.
Okay, sir.
Yeah, so that is to select a geotextile to meet the piping and the permeability requirements.
Okay, sir.
Okay.
Okay.
S- Sir, what Regina has told, if
Yeah,
we have value of O85 and
yeah,
O15, but
yeah.
we have to calculate O90 value. Sir,
No,
can we
it
use
is not
interpolation
to,
here?
no, sorry, it is not to calculate O90. So we select a
Yes.
geotextile that has an O90 of less than D85. It is not to calculate, but to select a geotextile having an O90 of this D85. Okay, if D85 is, let's say, 1.5 millimeters and D15 is 50 microns, O90 should be less than 1.5 millimeters. So any geotextile that has this O90 of less than 1.5 millimeters can be used for filtration purpose. Because in the market, you may have several geotextiles with the different O90 values. You may have woven geotextiles or non-woven geotextiles, and non-woven, within the non-woven, you may have needle punched or heat bonded or resin bonded geotextiles. So this the so what this criteria says is you select a geotextile that meets these requirements. Okay, here it is written geotextile selection for granular soils. Okay, so the O90 of geotextile should be less than D85 of the soil and greater than D15 of the soil.
Yes, sir.
Okay.
Okay.
Sir, basically here for piping limit, we are using actually we are comparing for from O90, but for retention limit, we have used O95.
Just 1 minute. Let me just yeah, actually these are yeah, from different published papers, and some people they work with O90 and some other people work with O95. So you'll see
Yes,
both
yes.
of them. In fact, there's no one single criteria. Like these are all from different collections. Like for example, this is the German recommendations, and this is with respect to D90, whereas there is another. Just 1 minute. Let me just see. Say zeroed. I think the zeroed or somebody he gives. Actually, 095 is also a significant factor, and there are some papers that work with 095, but 090 and
Sir,
095 are
but sir, O95 actually for O95 it
yeah,
was given as O95 less than equals to 2.5 of D85 like that.
yeah, that is another criteria. Just 1 minute. Yeah, here 095 is less than 210 micron. I think this is from some other publication, and
That's for clay soil, right?
yeah, a very I don't remember much because it's been a long time since I taught this particular topic. But basically, whether it is O90 or O95,
Okay, sir, no
it
issues.
is it is based on the based on different codal provisions.
Yes, sir.
Yeah.
Sir,
Sir,
I'm
one another question.
Yes, please.
Okay, okay, ask, please.
Regina, you may ask.
Yes, sir. Yes, sir. Sir, my doubt is how we can place the geogrid if we are constructing a embankment in soft soil, that is clay soil, and I am using geogrid in order to improve the interfacial friction. How I can improve the interfacial friction?
Okay, yeah, that's a good point.
Yes, sir.
Actually, um, we do not directly place a geogrid on a clay soil. We
Okay.
always put some working mat of at least 300 millimeters thick layer of what we do is on a clay soil, we put a separator, geotextile separator, and then placed at least 300 thick aggregate, and then only place the geogrid.
Sir, aggregate of what specification?
Aggregate is actually even sand can be an aggregate,
Okay, sir.
sand or stone
Ah,
aggregate. Like, say, if you follow the IRC specifications for roads, you use the IRC specs. Okay?
Okay, sir. Is it there in SP 59?
SP 59 is for embankments. And actually, let me just check. It's a good question. I do
Yes,
not
sir.
remember. Let me open that SP 59.
Okay,
Just
sir.
1 minute. Just 1 minute. Yeah, this is the SP 59, Geosynthetics in road pavements and associated works, right?
Yes.
And we see, I think they basically, you have the subgrade, then you have a geotextile, and then the sub-base material, base material. And the sub-base material and base material, they have their own particle size distribution, and then you have the wearing coat, wearing surface. Okay? Yeah, can you repeat your question? I seem to have forgotten.
Okay, sir. That is, I want to construct one embankment. My soil is soft clay, and
Yes.
I want to improve the interfacial friction between the
Okay.
soil and the geogrid. So, how I can place the geogrid?
Yes. See, you cannot directly place the geogrid on a
Clay
soft
soil.
clay. So
Yes,
you
sir.
have to provide a, a geotextile separator, and this
Geotextile is also required.
geotextile is required first, and then on top of that you put an aggregate, and then only introduce the geogrid.
Okay, sir.
No, otherwise, it will not work. Okay? Like for example, here we have the reinforcement layers shown as dashed lines. Then below this, we have the separators. Separator is basically a geotextile, and then you may also introduce a drainage composite. A drainage composite, it is basically for um, um, removing all the excess pore pressures.
Okay, sir.
So I don't think SP 59 has chapter on construction of embankments. Let me just. Yeah, actually it has. Yeah, I don't think your question is answered in this SP59
Yes, sir.
because it's basically SP59 is for pavements.
Yeah.
But there's another code. Let me just see whether it is there. Just 1 minute. This is the latest code of practice, geosynthetic reinforced soil structures code of practice, right? This what I have here is a draft, but basically it deals with the design of retaining walls and then the reinforced soil slopes and design of the abutments and so on. And let me just go to the embankments.
Sir, IS code number, please. Is it available online?
Yeah, it should be. Actually, it is okay. The code number is it's the textile committee TXD 30. Let me see whether it is 20465 or uh, let me. I think it is not. I will check up and I will send an email to you.
Ah, okay, sir. Okay, sir. Thanks a lot.
Right, I will.
I think it's not published. Top, it is given that drafts for comments only.
No, no, actually, now it has come back. It is, I'm
Okay,
not
sir.
able to find the final version.
Okay,
Yeah,
sir.
it was a draft in 2022, but now it has come out.
Okay,
But
sir.
I don't know exactly where I saved it. Um, but I
Sir,
think it should be just type the keyword, the geosynthetic reinforced soil structures code of practice.
okay, sir.
This is, and nowadays all the IS codes are freely downloadable. And you
Yes.
should be able to download this code also, code of practice.
Okay, sir. I will check.
Yeah, please check up.
Yes, sir. Sir, I have one more doubt. That
Yeah,
is related with the geotextiles.
yeah,
In sir's lecture, it was mentioned that thin geotextiles are used as separators and that for filtration. And thick geotextiles are used for cushion and drainage purposes.
yes.
So, sir, can you explain the difference between thickness of these two? That is thin and thick. It is mentioned.
Yeah. Actually, thin geotextiles, they are, we have this woven geotextiles, and they are very thin, about zero point 0.1 millimeter to zero point 0.2 millimeters. But their modulus is very high, their strength is very high. And we can use them as a separator, or we can use even for filtration. But they will not work as a drainage medium. And for drainage medium, let me just open another file. I think it is
Yes, sir.
there. No, just 1 minute. I've gone back to this IRC 59 document. And here you see the woven geotextiles and then the non-woven geotextiles, right? And then the geonets, geocells, and so on. See, when it comes to separation, we have a requirement for very high modulus. So we go for a woven geotextile. And then when it comes to filtration and then the drainage, we go for a thicker product. Just I think this is very difficult. Let me open my presentation. Just
Okay,
one.
sir. Okay, sir. Okay.
Yeah, okay. Can you see my slide?
Yes, sir. It's visible.
Actually, this is the setup that we have for checking for the drainage capacity of a geotextile. And we have the water flowing through the geotextile or geocomposite. And drainage applications, we want this to be as large as possible
Okay,
so
sir.
that we can have the flow. The area of A is the cross section of flow, that is the thickness multiplied by the width of the sample. Okay, like A is W times T, and so for having a larger thickness, the larger cross section available for the flow, we need a thick geotextile. Okay? And yeah, basically this is a very thick geotextile, and this particular test is checking for the radial flow.
Yes, sir.
I don't have any pictures of geotextiles, but I think they're all given in one of my presentations about the
Yes.
different varieties of geotextiles, woven and non-woven.
Yes, sir. It was there. Yeah.
Okay, I think already 5 o'clock.
Okay.
And if you do not have any questions, I want to stop here.
Okay,
And
sir.
I've scheduled one more meeting next week, Monday, and
Okay.
hopefully more number of students will take part.
Okay, sir.
Okay.
Thanks a
So,
lot.
okay, yeah, no problem.
Thanks.
And please send an email to me with any of your questions.
Okay, sir. I will send. Thanks.
Okay, thank you very much. Bye bye. Bye.
Okay, sir. Bye.
Okay, bye.